Invite people to move on, please. Thank you. Because we've got a lecture then. Thank you.
Sorry, you're right.
No worries, no worries.
Where can I sign the attendance?
We don't have any attendance.
We don't have to sign any paper. My friend say that they.
Today, for my lecture.
Oh, sorry.
No.
Have you left something on?
No worries.
Yes, no, cool.
Good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Now we are back in business. Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. 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 Most wonderful good afternoon.
Student card with the I'm not sure for the
Sorry?
I'm lost for student card.
You lost your student card? Okay.
If the some people cancel.
Has anyone seen a student card for that lady here? No? Okay, wonderful good afternoon, ladies and gentlemen. I think I tried again, hey? Good afternoon, ladies and gentlemen. Let's try it again. Ah, it works. Ah, brilliant. Yes. One more week to go, and then you have your deserved Christmas break. But I'm afraid before that we have a little bit more work to do, because next week on Thursday, as you all know, you have an assessment in this module. I've sent out an email to your Kent email. Please do check. There's all the information in it, right? I don't want anyone to post on the group chat on Wednesday evening. Does anyone know what's the topic of this test? I mean, if somebody does that, then my thinking is, well, evolution didn't know exactly what to do with you. Whether you are just, prey for some higher order beings, or, you might develop into something useful. So please read your emails. The test is a problem solving. It's not multiple choice, but it's open book, and you can bring whatever resources you need. I've sent you a list with all the topics that are potentially of interest, and we will go through a few topics in the second part of this session today. So I had a chat with a few students, and they said, oh, can you go through, for example, buffers again? And so we will do that. Yeah, doesn't mean that buffers will come up. I haven't done the test yet. Well, I have, but I can't tell you what's coming up. Okay? So, however, you also have to do a write-up for the PCR practical, most of you at least, for the BI 302. Oh dear, that doesn't look too good. Yeah. What did you do?
This game by multiple. Got taken out by a 6'10" guy. I don't want to jump.
Sports.
Not
yeah. Do sports or stay healthy. You have to do the PCR write-up, and there is a little bit of a data analysis section in this practical. And I really want you to look at that, because that will give you marks if you get this done properly. And in order to get this done, there are a few concepts that I'd like to discuss with you very briefly today. It is all about hypothesis testing. And that actually will be expanded upon next term. Next term, we still have some lectures for the BI 308, and that will be predominantly on data analysis. So watch that space. Now, we have started a little bit with data analysis and statistics, and I know that you all love it. So the combination of kinetics, statistics, and thermodynamics, that's sort of your ideal scenario, right? For an exam? Yes! Let's do that. So, I think we discussed in this module the concept of a confidence interval. And basically the starting point was that we take a sample. So that is a sample. We get some data, and from this sample, which is characterized by a sample statistics, so for example, the mean of the sample, which is denoted with this x bar, or the variance of the sample, which is denoted by s squared, or the sample standard deviation, which is simply s. And from this sample statistics, we try to make an inference when it comes to a wider population. And we said the population is characterized by parameters, for example, the population mean, mu, or the population variance, sigma square, or the population standard deviation, sigma. And basically, we don't know the population, but from our sample, we try to figure out what are these parameters. That's the whole point of basically inferential statistics. And just to debunk one of the myths, when people say, well, the population mean, for example, is not very well defined. No. It's not true. The population mean is an absolute, well-defined measurement. It's just I don't know it. But it's 100% well-defined. So if you want to watch porn, turn the sound down. The sample mean, for example, is absolutely 100% defined. Yeah? Population mean is absolutely 100% defined. There is no uncertainty about it. But when I try to figure out this population mean from my sample, that is where the uncertainty comes in. This is where I'm not entirely sure. So all I can really do is I can use my sample use this sample and try to guesstimate what is, for example, my population mean from that. And because it is an estimate, I can only say there's a certain range in which I believe this very well-defined population mean is located. So that is basically the concept of a confidence interval. This confidence interval tells me that in this range, let's say from 100 to 120, I am fairly confident that my population mean is somewhere in there between 110 and 120. And of course, this confidence interval depends on the sample. Or in other words, every sample has its own confidence interval. Because every sample is potentially different. Depending on what elements I pick from this sample, I get a different confidence interval. And that is what I sort of loosely described as the herpes of statistics, a sampling error. You can't avoid it. It's just simply there. You have sampling error, but it doesn't matter. It doesn't mean that you made an error or that you did something wrong. It's just simply the nature of the beast. This is what a sample is. It always has a sampling error, but every sample does have a confidence interval, where we say we believe that the true population parameter is somewhere in there. We discussed how you can calculate these confidence intervals for two particular cases. One case was a discrete data. And I told you, for example, this could be, in this particular case, it could be counts of something, counts in a temporal space. Can't think of anything better. It basically means we do counts, for example, per minute, or counts per hour, or something like that. That would be, for example, a call center. How many phone calls do we get per hour? Or how many gentlemen are going to the toilet within a 3-hour break, something like that. Doesn't work for females because, as we discussed, females have different toilet habits to males. Females usually go in clusters. And that's very important. These counts need to be independent. So with the ladies, usually it is, I need to go to the bathroom, and 5 others say, oh yes, I come with you. Because I mean, obviously it's a very dangerous route to the bathroom. And God knows what happens there. Whereas, you know, if you are a bloke and you announce publicly that you are going to the loo, and 15 other boys say, oh yes, I come with you, there's nothing wrong with that, of course, but you know, you might get some funny looks. So counts, for example, if you do measurements of radioactivity, yeah, these are typical counts whenever a radioactive element decays or an isotope decays. It is an event in a certain time point, in, let's say, decays per minute or something like that, or per second. So radioactivity would be something like that. Or it would be colonies per agar plate. You count colonies and you have them in a restricted volume, your agar plate, and that would be under this rubric. So we are counting, we do counts in a certain restricted time or space environment. And this would follow, usually, we said this follows a Poisson distribution. And we said calculations and a confidence interval for that is fairly easy to calculate. The confidence interval for Poisson distribution is just simply the counts that we have, and I abbreviate that with a C. You will be relieved to hear that I don't use K in this case. So we have C, that's the counts, and that is the total counts if I have more of these spaces to look at. Total counts, counts plus minus, bless you, 1.96 times the square root of the counts. And this is for a 95% confidence interval. Why 95%? Well, I want to be 95% sure that my true population count is in the calculated range. Why is it 95%? Well, it's just historical reasons. all the social scientists use 95%. Sometimes you will find that in sciences, people use a 99% confidence interval. And the more sure you want to be about something, the wider the confidence interval will be. So a 99% confidence interval will be wider than a 95% confidence interval. That's quite important. So if you've got, for example, let's say you have an experiment where you do, let's say, yes, you have an isotope of phosphorus, 32P, and very often it is written like that. This is a radioactive element that is very often used in biological research to label some biochemical compounds. Which compounds that you use quite frequently contain phosphorus? You've done it today. DNA. Absolutely right. DNA, RNA, you can easily incorporate 32P phosphorus into it, and it's like a sort of a label, because this 32P will eventually disintegrate, and it will give you counts. So, for example, you do 2 measurements, and you measure that you have 100 decays per minute, and let's say 96 decays per minute. So you measure that with one of these Geiger-Müller counters that go beep, 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 beep. And that basically counts every time one of these molecules decays, it gives you a beep. So if you want to know what is the range in which I would expect the true population mean for my decays, all you need to do is you basically sum them up. So you've got 100 plus 96, that gives you 196, and that is your count. And for the 95% confidence interval, you get 196 plus minus 1.96 times square root of 196. What's that? Square root of 196 is? Krish? 13? 14? Can somebody try that on a calculator, maybe? 14. Ha! So I still can do that. 196 plus minus, we'll just simply say 2 for that. 2 times 14. So it's 196 plus minus 28. That's the total count, but we really want to know the individual then. So we just simply divide this by the number of measurements that we have. So we would get 98 plus minus 14. Or our confidence interval would be from, what is it, 84 to 112. So in the long run, if we did this experiment, if we did this measurement for 10,000 times, we would expect that the population mean of our decays is somewhere between 84 and 112 decays per minute. Yeah? And that is how I want you to do things like that, should it ever come up in a test. Okay, happy with that? We also discussed what happens if we have continuous data, 95% confidence interval of continuous data. And continuous data, these are data where you can basically measure to the x decimal point. And we said the confidence interval, 95% confidence interval, would be the mean of the data, of the sample, plus minus a t-value times the sample standard deviation divided by the square root of the sample size n. Sometimes you also see this written as square root of variance divided by n. It's exactly the same thing. Both are known as the sampling error of the mean, SEM. And the t-value depends on how confident you want to be and how big your sample size is. And usually, so we say here confidence level. And instead of sample size, we also said usually what we use is the degree of freedom. Which in most cases is n minus 1. Now, I showed you how you can get a t-value with these t-tables, but you will be relieved to hear that I'm not expecting you to find a t-value in an assessment or in an exam. So if you have to calculate a t-value, a confidence interval for continuous data, I will give you the t-value. Yeah, so breathe easy. This confidence interval is something that you will encounter time and time again when you, in later years, read some scientific papers. Because it tells you in which range the true population mean is expected. Because let's face it, nobody actually gives a flying flamingo what your result is of this particular experiment that you did last Thursday afternoon. You were still hungover from Wednesday and could hardly stand up straight, and your partner just left with the cat and things like that, and your results are a little bit all over the place. Nobody gives a damn about that, about this experiment, about this particular experiment, about this particular sample that you did. But what we want to know is, what does this experiment actually mean in the wider context? And that's why the confidence interval is so useful. The x bar, the mean of the experiment, should you care to repeat it, is totally irrelevant, because that is particular for this experiment. The confidence interval will give you an information about the much bigger picture. Yeah? That is the point of a confidence interval, and that is why it is reported in the scientific literature. So confidence intervals are frequently reported. And yet there is another thing that is very often reported, and that is the p-value of an experiment. I sent out this question on the group chat this morning. Have you done p-values? I think it is part of the A-level syllabus, isn't it? P-values, is that right? So you really should all be familiar with it, but then a few people said, maybe not so. So let's just simply do a little bit of a revision of p-values. And you will be pleased to hear we don't, at this stage, we don't do any calculations today with p-values. So just sit back, relax, and enjoy. And in order to give you an idea about p-values, I want to take it from a totally different angle. Let's see, how can we do that? Okay, let's assume for a moment that, what's your name? Mel. Minal. Okay, let's assume Minal is accused of a heinous crime. What did she do? Well, what is the allegation? Minal allegedly has killed her lecturer in statistics. Right? And of course, because it is a legal system that we are looking at, Minal has been arrested, charged, and is now standing trial in front of a jury. The accusation is she has killed her lecturer in a sort of a rage of red mist because in the last assessment she got a really bad mark. How do we know that she did it? Well, next to the said lecturer, a knife was found. The lecturer died of 138 stab wounds. Yeah, that was the police. 138 stab wounds with a knife. The knife that was found has blood stains on it, and interestingly, it also has Minal's fingerprints on it. So now we are doing a trial. We need to find out whether Minal should be behind bars or not. You got the scenario? Yeah? Now, imagine you are a jury. You have to make a decision. What is your starting point? Is Minal, when you enter the courtroom, is Minal guilty or not? What would you say? What is the starting point in the British and most civilized countries' legal system? Is she guilty or not? Sorry? Innocent until proven guilty. So she is not guilty. Our hypothesis is Minal's guilt is 0. She is not guilty. Actually, this is called in statistics a null hypothesis. Null hypothesis because there is a 0 in it. She's not guilty. So, that's the starting point. And in proven guilty, we need to stick to this. What could be a possible outcome from the jury be? And we are talking about two possible outcomes because the crime happened in actually the little town of Canterbury, which belongs to England. And I make this because there's a twist to it. So what are possible outcomes that the jury can come up with? Guilty or not guilty. These are two outcomes for England. There's a third outcome in another country which is not too far away. Does anyone know what this third outcome is? Sorry? Second? Death penalty. Death penalty. No. We are not at the stage of penalties. Yeah? We just have to have a verdict. Guilty or not guilty. There's a third one. No? The third one is actually not proven guilty. Where would you find that? Not proven guilty. No, which place? You're right, but which place? It's in Scotland. In Scotland, you have the third option, not proven guilty. Not proven guilty actually means we know that the bastard did it, but he or she is too smart for us. We can't prove it, but next time we got you. Right? And we need to bear that in mind. But at the moment we are in the UK. So basically, not proven guilty means we do not have enough evidence to put Minal behind bars. Yeah? We need to keep that in the background. Okay, so these are if we stick with the two outcomes that we could have, guilty or not guilty, we now can examine the evidence and say, what is the probability with the evidence that we have that the defendant is actually guilty? Yeah? What is the probability that the defendant is guilty? Actually, if you think about it, we can't ask this question. Because if we ask this question, we would, in a way, say, we believe that she might be guilty. We are asking for the probability that she might be guilty. But that would be contravening our starting point. Because the starting point is, we believe she is not guilty. And if we all of a sudden say, what's the probability that she is guilty? That's sort of, you are biased then. And any solicitor would say, the jury is biased by asking this question. They can't ask this question. So how do we analyze this case? Well, instead of saying, what is the probability that she is guilty, we phrase the question slightly different. We say, never seen you so quiet. We ask the question, what is the probability that we observe the evidence? What is the probability that we find fingerprints of Minal's on the knife if she was not guilty? Bless you. Do you see the difference? We are asking for the probability that we find something while we still believe that she is not guilty. This is totally different from saying, what is the probability that she is guilty? What is the probability that that we observe these results, that we have the fingerprints? Now, turns out actually, what I didn't tell you was that the lecturer had a sort of visited, let's put it this way, let's go neutral, visited Minal in her student accommodation. She was just in the kitchen cooking. Just to say to her, look, bad mark in the statistics test isn't that bad really, yeah? But he felt really, really bad about things. And actually then, interestingly enough, his fingerprints were found on the knife as well. Would that change how you see the whole thing? With this additional information. First, what is the probability that we observe Minal's fingerprints on the knife that undoubtedly was the murder weapon if she is innocent? The probability to find these fingerprints is probably very, very small. Yeah? So if we say the probability of finding the fingerprints on the murder weapon, let's say, is less than 1%. Bless you. So probability, actually we abbreviate probability as just simply P. Probability that we find fingerprints given, and I abbreviate that with just a vertical line, given that she is innocent, is probably, say, 0.1%. Very small. If this was the only information that you have, what would you as the jury decide? It's very, very unlikely that you find the fingerprints if she was innocent. Would you say that she was guilty?
Depends if there's other evidence.
Okay. For the time being, let's forget what I just told you about the lecturer visiting her. Let's forget that. There's no other evidence. No other evidence. It's only the evidence from the knife. Would you say she is probably guilty? Yes? What's your name?
Chris.
Chris. Chris says she's guilty. Who else thinks that Minal is guilty if we have the fingerprints, the probability of the fingerprints, given that she's innocent, is less than is 0.1%. Who thinks, like Chris, she is guilty? Hands up. Yeah. Who thinks she's not guilty? Interesting. You are sort of a rebel. Yeah. Okay, 0.1%. That is sort of, I gave you this probability. What if it was the probability to find the fingerprints, although she is innocent? Let's say now we say it is 90%. Probability that we find her fingerprints on the knife and she is innocent is now 90%. Who thinks she's guilty? Hands up. It's interesting. Nobody thinks she's guilty anymore. Of course, we can say she is guilty just, just for fun. But you're absolutely right. With 90% probability that her fingerprints are on the knife, we can argue most likely she's not guilty. What about if I say 10%? The probability of finding the fingerprints on the knife is 10% even if she is innocent. Who thinks now with 10% she's guilty? Hands up. 10%. Should we put her behind bars? 1? 10%? 2? So 10% obviously you think she is not guilty. 90% you think she is not guilty. 0.1% you think she is guilty. Actually, there must be somewhere a cut-off, right? But this cut-off is more or less defined by you. At one point would you say, where do you think she actually should be behind bars? At what percentage? What do you think? 7? 70. So at 70%, there is a probability of finding the fingerprints on the knife And this probability is 70%, but she didn't do it. And you still would put her behind bars with 70%. Because we said it is somewhere between 10%, 10% people said, no, we don't think she's guilty, and 0.1% where people said, oh yes, we believe she's guilty. So it must be somewhere between 10 and 0.1. Where would you say she's guilty? Between 10 and 0.1. What's the legal term?
Beyond a reasonable doubt.
Beyond reasonable doubt. Have you been to court? I better not ask this question, sorry. Beyond reasonable doubt, you're absolutely right. So where's the reasonable doubt? Must be between 10 and 0.1. Where would you say?
5%.
5%. You just did me a massive favor. So, what's your name?
Ben.
Ben. Ben suggested 5%. Well, in a court case, this would be much, much lower. But let's say we do a cutoff of 5%. So, if the probability is 5% to get her fingerprints on the knife, and she is innocent, we say sort of. If it is lower than 5%, then we say it's unlikely that her fingerprints should be on the knife if she was innocent. So if it's below 5%, we say guilty. If it is above 5%, we say probably not guilty. Yeah? Does that make sense? This logic. Now we've got everything together for hypothesis testing. P, as you might have guessed, that's the p-value. And the p-value is defined as the probability that we observe the results of our sample. If we believe that the null hypothesis is true, that's the definition of a p-value. The cutoff point has a posh name. This is called the significance level. The significance level basically tells us at what point of probability we want to accept that she is not guilty or guilty. And the significance level usually is abbreviated with alpha. And the null hypothesis, this is usually written as I said, H null. This is what we said before we make the investigation. Null hypothesis is, in this case, is not guilty. So null hypothesis has 0 or a not in it. And we can say as a sort of a standard, if our probability value, if P is smaller than our alpha, than the significance level, we put her behind bars because we say she is guilty. we would say no longer H naught, H null, or H naught. Or we could say she is guilty, and we could formulate that with the opposite of the null hypothesis, and this is usually abbreviated as H1. It's called the alternative hypothesis. The alternative hypothesis is just simply the inverse of the null hypothesis. She is guilty. Next term, we will come across a slightly different modification of the alternative hypothesis, but for the time being, let's just live with that. So if P, our probability, is smaller than the cutoff point, we'll put her behind bars. We say she is guilty, and we accept the alternative hypothesis. H1 is accepted. What about I know it's really important to have this conversation, but it distracts people, and they won't love you for that. Thank you. If the p-value, if the probability is larger than the cutoff point, we say she's not guilty, so we not accept the alternative. And now we go to Scotland. We cannot prove that she's not guilty. She could have done it. But we cannot prove that she is guilty. So in this case, and that's a little bit of a sort of a mind twist, we have to say, we fail to reject the null hypothesis. She still could have done it, but we cannot rule out that she's done it, but we don't think she's guilty. So we fail to reject. Fail to reject and accept are two different things. If you think about it, it's a little bit like if I say, I love you, it's different to I don't hate you, right? You see the difference between that. It's a similar thing with I accept the null hypothesis, which means I have proof that she's not guilty, which we don't have, or I say we fail to reject the null hypothesis. Right? It's a lot of play with words. Now, how on earth can you remember that? There's a very simple way of remembering that. If P is lower than lower, if P is low, lower than alpha, H naught must go. If P is low, H naught must go. We reject the null hypothesis. If P is high, and you have to say that with an Australian accent, if P is high, H naught can't stay. Yeah, I know it's bad. I know it's absolutely bad, but I've heard people say that in the exam. So if P is smaller than alpha, we reject null and accept the alternative. If P is higher than alpha, then we fail to reject the null hypothesis. We don't accept it, we fail to reject it. The p-value itself is only a decision tool. Should or should we not reject the null hypothesis? The p-value is only a decision tool, and there's no further experiment that you can do, because that is all the evidence that you have. That is everything that Scotland Yard did. So if you see a paper, and very often this is in a paper, P will be expressed as, for example, P for that is 0.001. Accept or reject or fail to reject null in this case. P is low, H naught must go. So you reject the null hypothesis in this case. You see that in a paper. And then people say, well, we've got a p-value of 0.048. Reject or not reject? What do you think? Reject or not reject? We reject, because if we say our null, our cutoff, our alpha is 0.05, then 0.048 is below and we reject. But many scientists say, well, it's close to the rejection level, to the significance level. That means we need more experiments. Bollocks. You don't need more experiments, because that is all the evidence that you have. It's a little bit like the jury saying, no, we refuse to do anything because we need more evidence. So whenever you see a research paper where they say the p-value was close to alpha, so that means we need more experiments, just throw that paper in the bin, because they haven't done statistics properly. Yep. 7 minutes break, and then I will quickly show you how to formulate a null hypothesis, and then we do a little bit of revision. Okay, 7 minutes break. I hope as the course rep you didn't mind that I...
It's okay. The group chat's blown up though.
Really?
Yeah, it's
Why?
really funny. Me and Chris are good at it, apparently.
Was it I hope not horrible.
No, me and Chris are gonna fight after this.
What's that? Oh,
Yeah, we're fighting after this. Coming from.
how many? 53.
Yeah. Yeah, the group chat's kind of going off right now. I'm coming for you after this. I'm watching you. I can't with this group chat.
Please don't stab me now. No.
For some reason, I still don't get emails from you. Like, it doesn't send to me your emails. It doesn't come to
That
me.
was Jay.
Just actually, still it's not coming.
I have checked. Have you checked your spam folder?
Let me see, man.
I have double checked.
No, nothing comes in my.
And have a check with the help desk in the library.
Library, okay.
Yeah.
Alright.
Because I checked the last time and I can see email sent. Jesse and Chris.
Yeah.
Yeah.
Okay.
I recognise the name, but I don't know actually.
Just a quick question, is it too basic, this stuff?
No, I don't think for me it was good revision. Yeah.
Was good with,
Yeah,
okay.
yeah.
Good.
It was
Yeah,
Oh yeah, just a question. You know when we have a test on Thursday, and it's from 9 to I think 11, but on my timetable it says I've got a lecture 10 to 11. Is that? I'm a bit confused now.
right. What's happening is that they have to book the lecture theatres, or the rooms. And we have people who have extra time. The test itself is 45 minutes, starting at shortly after 9. So you should be absolutely good to go by 9:50. Yeah. But for people who have extra time, we still have to have the lecture theatres booked or the venues. So
We don't have lecture. So like we did.
I don't know.
The thing is today we all arrived at 9, and by the time everyone was we started at 9:30. We didn't start before that, and it wasn't like a school
Where was it?
in Wolf.
Ah, it will be in the sports center next week. Please check the venue. Yeah, and they know how to herd students in. STFU, sit down, no funny comments, right? Yeah. Was just a revision, the stuff. Nothing new. The p-value. That was new. No. P-value was new. But you have done the hypothesis. No. So that was new.
That was new, yeah.
New? Some.
Some of it, yeah. I mean, it just depends on the value, but it wasn't a bit of a brain twister.
Indeed, yes. Took me 5 years to get my head around that. And you have done that, Krish, yeah, at A level. Okay. But again, not everybody has done A level, yeah. Okay, very quickly I show you how you set up a null hypothesis. So for example, you have two samples, sample 1 and sample 2. And you want to know, are these two samples the same or are they different? Is there anything fundamentally different? The argument that you use is you say, okay, sample 1 comes from population 1, sample 2 comes from population 2. Population 1 is defined by its population mean mu1, and the same for population 2, which is defined by mu2. Your null hypothesis in this case would be mu1 population from, or the population mean from the population from which sample 1 comes is exactly the same as population mean 2. This means no difference. Between the samples, other than sampling error. Other than sampling error. You can also write this. I told you there is a sort of a null hypothesis should contain a 0 in it. So it's the same if you write it like that. Population mean 1 minus population mean 2 is 0. There's no difference in it. Yeah, makes sense? H1, you can do a really dirty trick. Mathematically, you can say is not equal. Or you can say mu1 minus mu2 is not 0. And you always start with a null hypothesis. Minal is not guilty. There's no difference between the two sample means. So you would phrase that here. There is a difference. Between samples. Caused by the obligatory sampling error. And an additional effect. Or an additional factor. As I said, you can't bypass the sampling error. It will always be there. But in the case of the alternative hypothesis, there is an additional factor. That the two samples come from two different populations, for example. That a treatment was successful, for example. For the PCR practical, you do a correlation between the DNA of the suspect and the DNA of the killer, and we will get her. Minal, we will get you. You know, we know who did it, but in the case of the lecturer, we couldn't prove it. But in the case of the victim and the suspect, what you have done in the PCR, you have done that in the PCR practical, yeah? If you plot the DNA as outlined in the statistics, you would get, hopefully, something like that, for example. In this case, your null hypothesis would be there is no correlation between the DNA of the victim and the DNA of the killer. And you could write that. How would you write? There is no correlation. What did we say? How do we measure correlation? What was the letter for it? Correlation. R. Pearson's correlation coefficient. No correlation, 100% positive correlation would give you an R of +1. 100% negative correlation gives you an R of -1. No correlation gives you an R of 0. Thank you. Your null hypothesis R equals 0. There's no correlation. That would be another alternative. That would be another example for null hypothesis. Alternative hypothesis R is not equal 0. Yeah? And with the instructions that you have in the PCR manual, you can actually, with the help of that website, you can find a p-value associated with your R, and you can say, right, if, for example, my p-value is, let's say, 0.68, I just make something up, 0.68, do we accept or reject the null hypothesis? If we say our cutoff alpha is 0.05 or 5%, p higher or lower than alpha? Of course, it's higher. So if p is high, H naught can die. So we fail to reject the null hypothesis, and we say there is no correlation. Happy with that? Can you do that? Brilliant. You get full marks for your PCR practical. Okay, quick revision what we have done with a focus what might come up in the test. We have done molarities, right? And I showed you this really nifty trick with the dimensional analysis, how you can convert things. So if you get, for example, something along the line of calculate how many grams you need of a substance in order to make up 0.1 molar solution, 100 milliliters of which, I really expect you to know how to do that. Yeah. Likewise, so molarities. And making up solutions. And of course, you have the link to my website with the questions and the videos. So please practice. We've also discussed the C1V1 equals C2V2 equation. And again, that is something that I really want you to know, because lots and lots of people in the final year bomb out on that again. It's unnecessary, because once you've learned it, hopefully you've got it. What else did we do in terms of molarities? I think that's pretty much, that was it. We did then move on to pH. I really want you to be able to calculate pH of a strong acid. How do you know if you've got a strong acid? Simply no pKa is given. And just as a reminder, because I know that some people find pKa a little bit cumbersome, pKa is an indicator whether the acid is strong or weak, whether the acid dissociates totally or only partially. So pKa high means weak acid. Only a bit dissociated. pKa low or not given, the acid is strong. Make sense? And we said pH equals minus log of the acid concentration. If it's a strong acid. If it is a strong acid and very dilute, we said pH equals minus log acid concentration plus 10 to the minus 7. The 10 to the minus 7 is the protons from the water. Okay? Weak acid we said pH equals 1/2 of pKa minus log of the acid concentration. That's the equation that you need to know for a weak acid. We then said, what if we have a mixture of weak acid and the corresponding base? We get a buffer. Sorry? We end up with a buffer, and for a buffer we have the famous Henderson-Hasselbalch equation, pH equals pKa minus log acid over base. Or you can use the rules of logarithm. You can turn it around and can say pH equals pKa plus log base over acid. Whichever way you fancy, feel free. So here on my website, you have plenty of exercise. Calculate the amount of acid and base required for a buffer. If I was you, I would probably have a good look at that stuff. Did I upset her? Have a look at that stuff. And what I want you to do, regardless, I always want you to do what I call a reality check. What do I mean by that? With a reality check, I always want you to check before you get started with anything weird and wonderful. Oops, good Lord, there's a lot going on. I want you to check, do we need more acid or do we need more base? In this example here, the pKa is 6.29. 6.29. The pH should be 6.48. So the pH is higher than the pKa in this case. Yeah? If the pH is higher than the pKa, you need more base. If the pH is lower than the pKa, you need more acid. So, pH lower than pKa, more acid. pH higher than pKa, more base than acid. If the pH is the same as the pKa, then you need exactly the same concentrations of acid and base. And I want you to do this check right at the beginning before you get the calculator out. And not just do that in your head, write it down. Because if you do the following, if you say pH is smaller than pKa, I need more acid, I then calculate acid over base concentration, and I find 5:1 ratio, for example, and I need 5 times more acid than base. It means it's probably correct what you have done. However, if you find acid over base equals 1/2, this basically says I need more base than acid. This is in contradiction to what you just said, I need more acid. Yeah? Total contradiction. Which one do you believe? Well, for the first one, the more acid, you didn't have to do any calculation. You just looked at it and made this decision. Should I have more acid or more base? There was no calculation involved, so it is quite likely that the second part, this bit here, that you made a silly mistake somewhere. Now, if you discover that you made this mistake, of course, you would try to rectify it and say, wait a moment, that can't be right, that doesn't look right, I know it's not right, so let's redo the calculation, see whether I tripped over a minus sign somewhere. If you can't find it, you just simply write down. I notice that there is a contradiction. What will that do? It will tell me that you thought about it, that you spotted the discrepancy. You might not have time to rectify it, but at least you showed me that you thought. If you just simply ignore everything, I say, well, you could have spotted that there is a mistake, so I can't give you any marks for the rest. Yeah, does that make sense? So please, 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 let me participate in the way you think about that stuff. I really don't want any other, participatory thinking events. Makes sense, yeah? Good. So we did buffers, we did spectrophotometry. Well, that's spectrophotometry, that's easy stuff, isn't it? So A equals concentration times the extinction coefficient times the path length. That's easy. We also then did a little bit of kinetics. And I can only say, first order kinetics, I love them. One of the things that we said in terms of, let's say, just for example, first order kinetics. Typical example is radioactive decay. So for example, I showed you how we can calculate and convert a half-life of a radioisotope, let's say 32 phosphorus that we had earlier. This has a half-life of, 14.2 days or something like that, if I remember correctly. We can convert a half-life very easily into a rate constant. And I showed you the trick for that. The trick is the definition of half-life equals natural logarithm of 2 divided by the rate constant, by k. Or if you are too lazy to put ln2 into your calculator, it is 0.693 over k, over the rate constant. And the unit for the rate constant, of course, would always be time to the power of -1, or 1 over time. So this allows you very easily to calculate or convert half-life into rate constants and the other way around. And we said, typical for a first-order reaction of that type, A is consumed, for example, like in a radioactive decay. we have our final concentration of A equals our initial concentration of A times e to the power of minus k times T final minus T initial. Or, if you rather prefer the logarithmic form, the natural logarithm of A final over A initial equals minus k times T final minus T initial. Okay, happy with that? Let's just quickly head over. So what could happen to you is that you get confronted with something like that. Maybe you will be asked to show me that this is actually, it could be, demonstrate graphically that this is a first order reaction. How would you do that? Well, all you need to do is really you need to convert this column here into ln 169, ln 152, natural logarithm 110, and simply then draw a good graph where you plot ln, these ln values versus time, and ideally you should see a straight line. And your argument is, that should be a straight line, by the way. And your argument would be, if I plot ln versus time and it gives me a straight line, it must be a first order. Can't be anything else. Yep, that's enough. Now, you see that I have hidden some numbers here in this table. And I haven't shown you the question, but the question, if you head over to the website, here the question would be, from the data given, not the graph, from the data given, calculate k and A initial at 0 and A initial at 200. How would you go about with that? First thing first, we need to find k. And the way you deal with that is you say, right, we had the equation ln A final over A initial equals minus k times T final minus T initial. That's the equation that I just showed you. And obviously you have that because you can take your stuff with you. So we can find k, we just need to define what is our A final and A initial and T final and T initial. And we can do that very easily from the table. All we need to do is we need to say, right, let's just simply take this pair of data and this pair of data. Oh, you don't see that properly. Let me. And we just simply define this here as our T initial, bless you, and this as our A initial in this case. And we define this as our T final and this as our A final. Yeah? These are the things that I've been given. And all I need to do now is just simply plug that into the equation. And I get natural log of 38 over 169 equals minus k times 150 minus 10. And from that, I just simply can calculate k. Ideally, you either do that, ideally you show me how you define things. So what would be great if you could say, for example, T initial equals 10 minutes, A initial equals 169 millimolar, T final equals 150 minutes, A final equals 38 minutes, a millimolar. If you make a little table, yeah? So how do we get now, let's say this question mark here? Again, we do exactly the same thing. I simply define the question mark as my, let's say, A initial. This is my T initial here. And I go for that, this bit here, as my T final. And this one is the A final. And the K I've just calculated. So I can say A final equals A initial e to the minus k times T final minus T initial. Now here, A final is 38 millimolar. T final is 150 minutes. T initial equals 0. And A initial equals, well, I need to figure that out. That's what I'm looking for. And K is what I just calculated. And with that, and this equation here, I can very easily solve this and find A initial. Yeah? So using this table mode, this one here, Using this table mode, this is incredibly helpful when you have to calculate something like that. It could very well be, however, that I just simply give you already an A final, A initial, T final, T initial. You don't have to figure out what to use, and you can calculate a K, or you can then calculate, what is my A initial, what is my A final, if that is required. Does that make sense? Any questions? When is he finally going to shut up? Now! Have a lovely weekend. Good luck for the test. If you've got any questions, group chat. See you on Thursday.